yeah, bicycle, yeah, bicycle. Okay, so we're here once again. We are talking about impulse momentum in Unit 7 here. This is one of our practice problems. It's number 3.4. And what we have here is a steel ball with a mass of 0.347 kilograms. It falls onto a hard floor and it bounces. So it falls down, hits the floor, and it bounces back up. Its speed just before hitting the floor is 23.6 meters per second. And just after it hits the floor, it's bouncing at 12.7 meters per second. You know, some energy was lost there. Things fall, boom, and then boom, 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 boom. Kind of a neat effect. We're looking for two things here. We are looking for the magnitude, or just the size, of the impulse of the ball. And then if the ball is in contact with the floor for a very short period of time, 0.0139 seconds, what's the magnitude of the average force F exerted on the ball by the floor? So let's take a look at this here. First, let's draw a picture, right? Pictures are super great. Grandpappy Botzer said so. So we've got a ball here, and it's moving down with an initial velocity of 23.6 meters per second. And then it hits the floor, and it's bouncing back up with a final velocity of 12.7 meters per second. If we would like to figure out the impulse on the ball, we also happen to know the mass of it here, 0.347 kilograms. If we want to know the impulse of the ball, well, we might originally think that, hey, impulse is just a force multiplied by a time, which I don't really have a force here, and I do have a time for part B, but I don't have a force. So, like, is this even possible? And yeah, of course it is. Instead of saying impulse equals Ft, we also know that impulse equals the change in momentum, which we've also written as the mass multiplied by the quantity of a final velocity minus an initial velocity. Remember, momentum is a mass multiplied by a velocity, something with a magnitude and a direction. That's a vector velocity. And a delta, a change in, is always a final minus initial. So when we pulled the m out, we get m times the quantity of Vf minus Vi. So if impulse, J, which we're looking for in part A, is equal to this, and we know masses and velocities, let's just use that, find the impulse. So going through this here, we have, let's see, the mass here is 0.347 kilograms. The final velocity here is 12.7, and the initial velocity is 23.6. And that should give us the impulse, right? Well, if you just wrote this down, you have made the classic introductory physics mistake. It's a mistake a lot of people make. Can you find it? Pause the video, see if you can find the mistake here, because something is wrong in this impulse equation. See if you can find that. Did you think about it at all? Okay, so what was the mistake that was made here when we wrote this out? Well, velocity is a vector. It has both a magnitude and a direction. And because it has both of these things, especially the direction, we need to consider the ball is going down in the beginning and it's going up at the end. And because that direction has changed, we need to choose positive and negative directions. Now, it doesn't matter what direction you choose positive. You could choose up as positive. You could choose down as positive. It doesn't matter. What matters is that the other direction is the opposite of that. The other direction would be negative. So let's just make up positive, and let's just make down negative. That's the thing that most people pick for things. It doesn't matter, though. But if we do this, what we see is that our up direction's positive. That means this is a positive 12.7, so nothing changed. But we are subtracting a negative 23.6. And subtracting a negative number is, well, it's addition, right? So we need to make sure that we're actually adding these numbers together due to that sign convention, due to the way that things are going to work out. So it's a very important thing there. It's the thing that everybody tends to make as a mistake the first, one or two times they do a problem like this. Don't make that mistake. That's also a huge reason why we drew the picture here, because the picture shows us the magnitude and the direction, okay? So let's work this out. We'll do the addition of 12.7 and 23.6 first. So 12.7 plus 23.6 gives us 36.3. So we've got 36.3 here. And then we multiply that by the mass, which is 0.347. And that gives us an impulse here of 12 let's just round up, 12.6 Newton seconds. Okay, that's an impulse unit, or momentum unit, Newton seconds. So that is part A there. We have the impulse. In part B, though, we are looking for the magnitude of the average force. We're looking for F here exerted on the ball. And luckily for us, we've already written this equation out. We know that an impulse equals a force or an average force multiplied by a time. We'll talk about in some of the later videos when we have graphical force time graphs, why that's an average there and how, if you actually wanted to find an impulse, it'd be an area under a curve. But if we know the impulse, we know the time, we can solve the average force. Nothing too crazy there. So let's go ahead and do that for part B. Like I stated, the impulse is equal to an average force multiplied by some time. Our impulse is 12.6 Newton seconds. This equals F multiplied by the time, which was up here, 0.0139. So 0.0139 seconds. And if we just quickly solve this, we divide by the 0.0139 seconds. When we do that on each side, the seconds go away, which is nice. Our force will be in newtons. Since we're dividing by a fraction, we're going to get, or a decimal, we're going to get a larger number here. So 12.6 divided by 0.0139 gives us a force equal to 906 we'll just round up and say 5 newtons. And that's it. That's how you go about this problem. It's just a conservation of momentum. It's a force impulse, or it's an impulse momentum equation. The big thing is recognizing when directions change, you need to consider the value that it's a vector and that some things might be positive and some things might be negative. But that's it. We're finished. Hopefully that problem was pretty straightforward for you. Hopefully you enjoyed it. And next time, we'll be going to Mars. But until then, adios and take it easy.